In this tutorial we'll be looking at circular motion in uniform circular motion, that is, in a horizontal plane, particularly focusing on inclined banks, which seem to be the more challenging of questions. So first of all, if we've got an object on an inclined plane, there really are three physical forces that are operating. The first being the force due to gravity, or the weight force. The second is the normal reaction force, which is perpendicular to the plane. And the third is the friction force, which is operating down the incline. Now remember that this is a side profile of a vehicle that has a centripetal force as a resulting force. As such, it's horizontal uniform circular motion. What we need to do first of all to understand what's happening in terms of forces is resolve or break down our angled forces into horizontal and vertical components. So you can see here that the normal can be broken into a right angled triangle. Importantly, that right angled triangle has exactly the same proportions and angle as that of the inclined ramp. It is a similar triangle. So they can be broken into a vertical and a horizontal component. The horizontal component, using some basic trig, where the hypotenuse is the normal, we see our opposite side of our right angled triangle is n sine theta. And likewise, the vertical component, using the yellow right angled triangle, n is our hypotenuse, and the adjacent gives us a function of n cos theta. Our frictional force can also be broken into a horizontal and vertical component. And likewise, it too makes the same angled right angled triangle. It is a similar triangle with the same proportions and angle to that of the ramp. It can be broken into horizontal components and vertical components. And again, using right angled triangles, we have on this yellow right angled triangle a hypotenuse of the force due to friction. The adjacent side gives us a function of force due to friction cos theta. And our vertical component is force of friction sine theta, because it is the opposite side of this right angled triangle. So now we have a weight force operating down, an angled normal reaction force that can be broken into a horizontal component n sine theta and a vertical component n cos theta, and a friction force on the angle that can be broken into a horizontal force of friction cos theta and a vertical force of friction sine theta. Let's consider all the forces in the vertical direction. So first of all the forces operating up, which is just simply n cos theta, they'll be equal to all the forces operating downwards, which is the force due to gravity, plus the sine component of the frictional force. Now this object is not lifting off the track or falling through the track, so the vertical forces upwards are equal to the vertical forces downwards. And that's our very first equation we can use later on. Secondly, horizontally, we've got forces to the left, which is n sine theta, and the cos of the friction force. Now we don't have anything going to the right. That is equal to our net force, mv squared on r. So again, recapping, the up forces, n cos theta, balance out and are equal to the sum of Fg, the force due to gravity, and friction sine theta. So the object is not moving up or down. That leaves us the two left-directed forces, n sine theta, and the cos of the friction force operating into the centre, which of course is equal to the centripetal force, mv squared on r. In summary, there's our two statements in terms of horizontal and vertical forces. Now let's apply this to an example. As you can read, we have here a vehicle that's travelling at 30 meters per second that can take a bend without having to rely on sideways friction because a banking or an angled track. The radius of the curvature is 12 meters, and we want to know at what angle should it be banked. We don't have any frictional force in this example. If we go back, it says without having to rely on sideways friction. So we really only have our force due to gravity, or our weight force, and our normal reaction force. We have a velocity of 30 meters per second, radius of 12, and we want to know what is the angle theta. So again, our angle component we break into a horizontal n sine theta and a vertical n cos theta. And we can see that the vertical, all the forces upwards, well, there's only n sine theta, is equal to all the forces downwards. And in this case, without the frictional force, it's just the force due to gravity. We're going to call this equation 1. Now looking in the horizontal direction, n sine theta is the only force operating in the horizontal plane, so that has to be equal to the centripetal force, the net centripetal force, mv squared on r, and that's equation 2. So here we have equation 1 transposed, making n the subject. When we divide mg by cos theta, we're left with n, the normal reaction force, is equal to mg divided by cos theta. We're going to call that equation 1a, because it's a manipulation of equation 1. So we have equation 1a, and I want to substitute that into equation 2 that we derived earlier. So there's equation 2. Now if I substitute in n equals mg cos theta, where the n was, I am left with mg over cos theta times sine theta equals mv squared on r. Let's group our sine and coses together in the one fraction and multiply that by mg. That's just a slight rearrangement of what we have here with numerators and denominators. Sine over cos is a tan function, so we can simplify that to tan theta equals tan theta multiplied by mg is equal to mv squared on r. You'll notice we've got mass on both sides, m here and m there, two common factors we can divide through. That gets rid of our mass. Now to get angle by itself, we need to get rid of this times g. So we'll divide g over to the other side. So we end up with tan theta equals v squared on gr. Now to find theta, we simply take the inverse tan of v squared on gr. So here's our starting equation to solve a problem. Let's substitute in now our variables for v, g and r. V was 30, g is 9.8 meters per second, or newtons per kilogram rather, and our radius was 12. Putting that into our calculator, we end up with a banking angle of 82.6 degrees. Not very practical, quite a steep incline, but that's what would be required for a vehicle of 30 meters per second to go around a radius of 12 meters with uniform circular motion. I hope that's been of some help. Study hard and get your best results. Bye.